So let us do the hardware implementation for the 16-bit adder. As we have observed that the adder configuration is 16-bit, I have to give the A and B with the size of 16-bit. So totally there are around like 32 inputs that I have to provide to uh, like verify the functionality of the 16-bit adder. So after we do the implementation on the FPGA for the 16-bit adder, as we see, this is what a 16-bit adder I will be implementing on the FPGA core, where I have to do the hardware simulation through giving a combinations of around 2 power 32 inputs. So 2 power 32 combinations that practically not possible with 16 switches. So I need to have 32 switches. So there are around like 5 push switches also if I add it. So 16 plus 5 it's around 21. It's not practically possible with giving a 32 input combinations and doing the hardware simulation for the hardware module which I have it 16-bit adder. So now what I do is I will be using the option that I have it on the Vivado, that I can use a integrator block where I can integrate the ILA as well as VIO. There are like two dedicated integrators, that modules in IP modules that we have it. With the help of these two, and I will be adding my RTL block. This is the entire RTL block. I will be integrating these three blocks and I will be creating as a HDL wrapper, and that I will be creating as a top level block, and that top level block will be added with the XDC file, user constant file, and with that I will be doing the dumping process as usual like we have known in the previous session. Now coming to the RTL block which I wanted to implement is, so as usual like we have a 16-bit adder which add like two inputs. It's a simple program that I can write it where it generates the carry and sum. But the question is the sum which is the size of 16-bit where to be displayed. So that's why what I do is there on the FPGA I have a 7 segment display which will be the 4 digit, digit 1, digit 2, digit 3, digit 4, and I wanted to display my 16 bits output sum on the 7 segment display. So for that I wanted to check the schematic of the 7 segment display where it will be driven with the Artix core with 4 inputs as anodes, 8 inputs as a cathode. So it means 8 inputs and 4 outputs, right? It means it means I have to generate this is what RTL block which I am trying to implement as we discussed, and VIO block, virtual input and output block, and the integrated logic analyzer. These three blocks I will be creating it over here, and I will be integrating them, and I will be creating as a HDL wrapper, and I will be making it as a top level block. So this top level block added with the XDC file, and with that I will be dumping the FPGA program, like whatever the bit file I will get it, and I will be dumping on the FPGA core. So it will be like loaded into the FPGA core which we can see it here. Yes. So now coming to the RTL block where I can show it over here. This is the RTL block where I wanted to implement the 16-bit adder, and I will be generating a sum of 16-bit. So I will be loading the 16-bit into the 4 bit size. This is the first 4-bit, and this is the second 4-bit, and third and fourth. Like this is how like I will be dividing the 16 combinations that output that we have into the 4 sub combinations, right? So that 4 sub combinations where we have each which will the size of a 4-bit, I will be loading into the module. This is what the module called a 7 segment display. Like this is what the module called 7 segment display, where I need 4 outputs, right? This is the entire block is the 7 segment display module where I need like 4 outputs will be generated as a anodes, and the same way 8 outputs generated as a cathode. Means there is some logic we have to implement on this one, so that for the given inputs there should be anodes and cathodes should be generated such a way that whatever that expected logic need to be implemented on this one, yeah, whatever the expected logic it need to be implemented on this one. As we can see, if there is a anode with one pattern like a dedicated pattern like there is a digit 1 is high, and here 0, here 0, here 0. If I generate an anode, this is where I have to design an RTL block which generates the anode and which generates the cathode also. There is an anode of 4 bit and cathode of 8 bit. So once that anode of 4 bit as like 1000, there will be a first transistor will be turned on, so that whatever the supply that we have, it will drive the first segment. So this is what first digit, we can say it is a first digit, and this is the second digit, and this is what my third digit, this is what my fourth digit. So as we know that once that transistor is turned on, that VCC is provided, the anode over here it is high, and there are like dedicated cathodes will be there for the 8 displays that we have, 8 segments that we have. This is what your block over here, which will be a internal block of this digit. So when we give that 8 combinations over here, 8 ports over here, 8 cathodes over here, which will drive the 8 cathodes over here, which will be located over there in each and every segment as over here. Like A will be displayed over here, B will be displayed over here, C, D, E, F, G. Now, for example, I wanted to display a logic 0 over here. Logic 0 in the sense this should be high, it need to be turned on, this segment should be turned on, this segment also need to be turned on, this also need to be turned on, and in the similar way like this one and this one. This is how I can display the logic 0. Except G and except DP, other LEDs need to be turned on. Means all the cathodes over here, as we know, anode should be at a high potential and the cathode should be at low potential. There will be anode high and cathode low. That particular diode will be coming into the forward, so that we can see that there will be a turn on case for the particular diode or particular segment. So like that, what I have to do is there is a corresponding A location need to be turned on, so that A should be 0, B should be 0, C should be 0, D should be 0. Like that, up to here everyone should be 0 except this one and except this one. Means A to F all need to be 0, all cathode patterns need to be 0 except G and DB. So this is what the pattern that it has to generate. The RTL block need to generate this kind of pattern for displaying a logic 0 across the first location. Now if I see that equivalent value when we have a 4 bit of 000, which is the hexa equivalent is around 0, and for this one 0011 there is a hexa equivalent with 0 3 0 and 3, there will be 0 3 is the equivalent cathode display value, right? Equivalent cathode display value, where we can see it over here. The program is written like that. When the BCD input is 0000, means like I wanted to display a logic 0 across this one. I wanted to display a logic 0 across the 7 segment display. What I need to do is there is a cathode pattern I have to generate like this. There is a pattern of 0 and 3. There will be 0000 and 0011, right? So this kind of cathodes around like 8 bit, if it generates, automatically 0 will be displayed. So in the similar way, when we wanted to display 1, there is a particular pattern of cathode need to be this one, and if it is need to be displayed 2, there is a particular cathode of this one. So like that I wrote a code for a 7 segment display. Once like a BCD input is given, how the cathodes need to be generated. So this is what my cathode generator block. Yes, we can see that the cathode generator block, what it will do is whatever the particular inputs that we give it 4-bit data. So as per the 4-bit data of BCD, it will be generating a cathode pattern which will drive the 7 segment display. In the similar way, there is a anode also need to be generated. As the anode and cathode, if it is generated, there is a 8-bit along with the 4-bit. 8-bit along with the 4-bit, there are around like 12 bits data that I have to generate, so that there is a particular display that we can see it on the FPGA. So this is the entire code. So we wrote it like a clock divider circuit on one particular purpose, where we can see that as we observe one thing, as we observe one thing there is a first digit, if it is turned on, a cathode is active, the rest of the digits are like turned off. There is nothing is displayed across this one because there is no anode active. So only when that anode is active, the particular display we can see whatever the cathode it generates the pattern, the particular pattern we can see it across the particular digit only when that particular transistor is turned on. So now one thing I have to observe is the cathode pattern, it will drive only one display, it's not at a time for all. So that whatever like you wanted to drive, let us suppose I wanted to drive the data sum is across this one, sum is let us suppose 1023 plus and 10011. Let us suppose I want the sum around 1034, means 1 need to be displayed over here, 0 need to be displayed over here, 3 need to be displayed, and 4 need to be displayed on this one. So when we are wanted to display all the digits at a time, it's not practically possible. All the transistors we cannot turn on. Even we turn on also, these segments like 8 we have it, it will not know right where to be displayed, because that 8 segments right which can drive only one digit at a time. So once we observe this one, what we have to go with the alternative is, so we need to design a circuit such that there is a selecting module that I have to design, which will be selecting that each and every we will be selecting that each and every digit one after one. It's not at a time all. So one after one, in the sense, as we see that if the particular pattern is done on this one, so meanwhile the rest of the things will be turned off. So after immediately this one will be happening, and after immediately it will be happening, after immediately it will be happening, right? So as it looks like multiple frames, where like this one is displaying as a first frame, and this one will be displaying in the second frame, this one will be displaying in the third frame, like that we have 4 frames. It will be moving one by one within the snap time, or snap time that I cannot detect. Within the snap time, if the frames are moving, as we can see that multiple frames will go within the snap time, we can see it as a video. So as like it is like a video where one will be repeatedly on and off, but that off moment we cannot see. So we feel that 1034 will be displaying every time. So for that what I have done is, the counter circuit which I generate, and I have generated the pattern 00011011. Once the 00 is generating, the anode module and cathode module will drive the first digit. 01 it drives the second digit, 10 it drives the third digit, 11 it drives the fourth digit. So this is the particular pattern, right? As per the counter circuit which I have designed, there is a frequency of around 15. So we can see that the frequency is around 15. So as this frequency is nothing but as we have the clock frequency of the particular FPGA kit is observed as, we can see it, we can go through the manual and we can see that user manual says that the clock frequency it is around 50 megahertz. So now what I do is, I don't need this much frequency. What I need is, as the snap time it will be equal to the 3 hedges, right? 3 hedges in terms of frequencies. I will be converting that high frequency to the low frequency by the clock divider circuit. So what I do is, I will be designing a counter circuit. I will be designing a module with the 15 combinations that I will be putting over here, and I will be designing a new clock, right? It generates with the frequency of 15. So it will be a counter with 2 bit, means 2 power 2 uh, like divided by the 2 power 2. If it is a 4 bit, divided by the 2 power 4. If it is a like a 16 bit, 2 power 16. If it is a 15 bit, I am taking it as a consideration, right? 2 power 15 times that input signal will be divided, right? So means this is what the frequency as we give it as a clock. A new frequency which I generate across the clock divider is a frequency of clock divided by, so 2 power whatever the frequency it can divide is like you can mention it here, and it's up to you. You can change this one. If you change it to like 2 power, I have done the iterations, I changed it to 2 power 25 and 2 power 21 and 2 power 16, and I changed for every case, and I observed like where I could get the proper clarity across the 7 segment display. So 2 power 15 means there is around like the input frequency, if it is around 50 megahertz, and it will be divided by 2 power 15. So that is the clock we can see it here. So that frequency at which this pattern will be generated, 0 0 which drives the first digit, 0 1 drives the second digit, 1 0 it drives the third digit, and 1 1 it drives the fourth digit. So all the digits are displayed one after one. It's like each frame will be moving with one small frequency snap time within the snap time, so that all the frames will move within this frequency. Then only we can see the proper display. So all the digits will be displayed over here, and as we write the code for this module, this module clock divider and counter, the selection modules, anode generator and cathode generator, if you add all these blocks, automatically whatever the inputs that we give it, first input will drive the first segment, second input will drive the second, third, fourth, like that all the digits will be displayed, and whatever the 15 bit or whatever the 16 bit sum we have, that sum we can see it on the 7 segment display for sure. This is what the 7 segment display, whatever the 16 bit sum that we have it, 4 bit sum, first 4 bit will be seen on this one, and second 4 bit it can be seen on this one, like that 16 bit we can see it on this one, that sum we can see it on this one. So that is what we have to check it. There I have to create like the adder module, and this all modules combined as one block. So this is the code, I have it over here. I wrote the code on for the 7 segment display. This is the 7 segment display, as we have the clock block, this is the clock divider block, and this is the counter block, this is the counter block, this is the module where like selection will be done, and anode generator and cathode generator. This is what the anode generator module and cathode generator module. This is the cathode generator block, right? Yes. So now let me copy this one, and let me create a project. Yes. So let me create a project. Next, and the project name, I wanted to create a project in E drive. U1 is the project folder that I wanted to save. Under U1 I wanted to save with the project name is sum underscore 16 U2. Yes. So this is the name that I wanted to put for the project, and I will be loading the project into the E drive in the folder, dedicated folder U1, and give next. And RTL block that I wanted to create, like I have to do the project of RTL, right? I have to select the FPGA which I wanted to do the implementation on. So this one I have to give next, and let me verify the port details which FPGA kit I wanted to dump, that all the details need to be correct. Verify them and give finish. And now we add a design source and create a source, like Verilog module that I wanted to create. Adder underscore bottom, right? It's not a top block, sub block. Yes, like sub block. Yes, create sub block. Let me create. Add a sub block. Let me create. Yes, finish. The ports that I wanted to give it manually, so let me skip. Yes, this is the module.vib file that I can create. The text window let me open, and where let me write a program. This is what the program that I wanted to write it for the adder subblock. Yes, this is what my adder subblock. The name of the module is adder sub. Yes. So what code I wanted to write is it will be A comma B, the two inputs, and the sum comma carry, these are the two outputs. Yes, and inputs are A comma B, input sum comma carry. So we can see that there is a B inputs, sum and carry, these are the outputs, and the size I have to mention it properly. The size of the sum is around 15 bit, 16 bit, 15 down to 0, and carry is the 1 bit, and A and B are also of 16 bit, so 15 down to 0. Yes. Now actual logic that I have to implement across this one is assign the concatenation of uh, carry comma sum as the actual sum A plus B. I don't want to go into the details, like I don't want to make that logic complicate, so just let me add a sub block like this. So now what I do is I have to add some extra block over here, that adder block, and this enter block, as I have a code of this one, right? Let me copy. I wrote this one, I've used in the last session. Let me copy this one. Yes, so this is what the enter block, SSD block, generator counter multiplexes. This is a cathode generator, anode generator. Yes, so let me save. Yes, as we see, this block is implemented, and this block also implemented. So now what I do is, we can see there are like two separate blocks were implemented. Now I will be creating a top level block, module. I have to create this top level block, adder sub block, and now I will be creating this one as a adder top level block. So let me give that module name is adder top, where the inputs are A, B, these are the two inputs, and for this block it needs around clock and reset. This two will be the two more inputs, and sum and carries will be the outputs, and anode and cathode also outputs, which will drive the 7 segment display. So anode and cathode and sum and carry, this all comes under the outputs. A, B, clock and reset, this will comes under the inputs. So let me mention them, A comma B, the two as inputs, and the clock also as inputs. RST also comes under the inputs, and the sum comma carry comma anode comma cathode, these all comes under the outputs. Yes, so let me declare A comma B as inputs, input 15 down to 0, A comma B, and also clock as inputs, and reset also my another input, and output wire anode cathode sum and carry. So these are the four outputs that we have. Carry is the 1 bit output, and the sum is 16 bit outputs, 15 down to 0, and cathode is 8 bit, right, 7 down to 0, and anode is 4 switches that we have, 4 transistors that we have to drive through the anode, so 3 down to 0. So these are the four outputs that we have it across the top level block that we have. So this ender block I consider as this one, ender block I consider as a top level block, adder top. Right now I have to integrate this through the integrated that we have it across the Vivado. So these two blocks I will add it. So first of all, let us verify that whatever the code we wrote it is correct or not, right? Yes. So now port declarations are done. Yes, I will be doing end module and the module, and here we have to call the modules, like when we wanted to bring the two modules, top level block I wanted to implement, in the sense this block and this block I have to integrate, right? So I have to use the structural modeling style, uh, like instantiating this module and instantiating this module into the top level block. So instantiating this module, add a circuit. Yes, also I have to instantiate this block also, right? So these two blocks I will be calling over here, and I will go with the labeling L1, L2. That's what labeling is done. And the port mapping point of view, the A, B will go to the adder circuit, sum and carry will be generated, these are all two outputs, right? And also the same sum I wanted to see it across the 7 segment display. So where the 7 segment display, where the switches of around 16 SWF16, that sum I have to send it into this one. So now what I do is that SW I have to now change it as a sum, right? So now so there is a adder block and a SSD block, 7 segment display block. That will be two blocks that as L1 and L2, which are called into the top level block. These are like a top level block which will be a like which is created across the design sources. Yes, so if you see that there will be L1 and L2, these two modules will be sub level blocks for the adder top, right? So now what I do is I have created up to here, I have to add that ILA block and VIO block now, right? So what I do is I will be using that IP integrator over here, and let me create a block design. The block design is adder test. So I will be creating as a adder text to like create a test module where like design name is like test module. Let me give OK. There is a block will be created with that name, adder text. Testing means this block will be tested now, will be like simulated now through this ILA and VIO. So that's why this total block I call it as a adder top. So like adder top is this block, and adder test will be this block, right? So now adder test block will be like this, and now there is an option that we can add whatever the blocks are required. So now give right click and add module, right? Add module, where I can see that adder top is the module that I wanted to add. Give it OK. Means so into the top level block, into the integrator, I will be adding this adder top. So I have adder top. This is what RTL block is added. So you can see it here. There is the three modules that I have to integrate here. Three blocks I have to integrate here. One is the RTL block, which I have made it ready for the adder top, and these two modules that I have to integrate. I have to add these two blocks also. So one is go with this option. One is VIO. This is what VIO, and there is an option like a control Q. If you press control Q, the IP details you can see, IP block which you are trying to add, the description for the IP block you can see. So there is an option like control Q, so that we can see that properties, otherwise you can close it. So give double click so that VIO block will be added here. In the similar way I have to add ILA block also. So integrated logic analyzer also. Yes, so I have created like a there is a block design that I have, on which adder top is there and VIO is there and IL is there, virtual input output. So through which like I will be giving the inputs. Actually previously we observed one thing that there is a problem with the number of switches across the FPGA. So we didn't find the 32 input switches from the FPGA. That's why what we do is, to do the hardware implementation and verifying the functionality across the hardware, we are trying to use this IP block VIO, virtual input output block, through which like I will be giving the inputs to do the hardware simulation. So now let me go with the maximize this one, right? Now for that, let me make the clock will be external. So this is what my clock, I have to make it as external, right? Because like I have to take the clock signal from the FPGA. As per that FPGA clock itself, we have to do the functionality, and that functionality is done for the display module. That display that we have to see it across the same FPGA. So the clock we can see it across the N11, the same clock we have to take it, and we have to give it over here where we have 3 blocks, and the inputs will be given over there inside, and we can see that output, and that output we can display across the 7 segment display. So now what I do is the same clock which is considered as external clock, that we have to connect it with all the blocks which we have it on the integrator. Yes. So now if you give the double click on this one, and when it is asking for the number of ports count for the input as well as output, so what I need to do is that VIO block has to generate the outputs from where like it generates the inputs to this block. Means this need to generate the inputs to this one. So that it needs to have that how many inputs that RTL block has, A and B and reset. These are the 3 inputs that it needs, so that a VIO block also need to have 3 outputs. The similar way, what we need is that sum and carry that we wanted to see it over here, so that I will be taking that sum as well as carry as 2 inputs. Sum and carry as 2 inputs. So let me go with the next tab, where like the probe inputs and probe outputs. As I said, like a probe inputs, sorry, the input probes is 2, because like we have to take 2 inputs to be considered as a 2 outputs as considered as inputs, and I need to generate 3 outputs over here, like 3 inputs over here from the outputs of this one. So outputs will be 3. So now if you see this one, inputs will be a sum as one input, which will be the size of 16 bit, and the carry is the one input, it will be the size of 1, right? As well as that output ports are, right, I have to generate 3 outputs. One is A, another one is B, another one is reset. So A is a 15 bit, B is also a 15 bit, sorry, 16 bit, B is also a 16 bit, and the output will be a size of 1. That reset need to be as 1 bit. Yes, give it OK. So automatically the ports will be updated with the how many port requirement that we have. So what I do is I will be generating a 16-bit output as input, which need to test it over here for given input. So this one need to be connected over here, and this one need to be connected over here. Yes. In the same way, the sum you wanted to see it over here across the probe, and the carry you wanted to see it here. And this one will be considered as external, because like this anode and cathode need to come outside. See, so when I'm creating the 3 blocks over here, there will be 2 outputs has to come outside. The 2, as one is anode, another one comes as a cathode. Means this block is totally connected with the 3 ports. One is anode, another one is cathode, and there is a clock as input. So we can see this one is one external port, and these 2 also considered as a external. Make it as a external, and this also make it as a external, make it external. So these 2 ports will drive the 7 segment display, and this port will takes the inputs from the clock. There is a dedicated oscillator we have, from which it takes the input. So these 2 blocks are integrated, that's okay. And now coming to ILA, where ILA is nothing but integrated logic analyzer, across which we can see that outputs, right? So keep it in negative, and number of probes that you need is around, we can see it, the probes need around, so we wanted to see what are the things that you wanted to see. You have to add that many ports. A you wanted to see, B you wanted to see, reset also you wanted to see, sum and carry also you wanted to see. There are around like 5 ports that we wanted to see, so keep it as 5, right? The probes which need to be, right, some A I wanted to see it here, which will be the size of 16 bit, B you wanted to see it here at the size of 16 bit, and reset over here, and the sum will be around 16 bit. You wanted to see it here, and carry will be 1 bit. So that give it OK. So automatically this will be the block will update with this many ports. So A you wanted to see it here, and B you wanted to see it here, and this is what the reset port that the status of the reset you wanted to see it here, the status of sum you wanted to see here, and the status of carry you wanted to see it here. Yes. So now validate the design. If there are any errors, it will show it as error. Okay, no errors, and you can reconfigure it once properly. So this is how we have created a 3 blocks over here, right? These 3 blocks now it will be created as a top level block, right? Once I go with the minimize this one sources. So this is what your block design BD. Now we have to convert into the HDL wrapper. Give right click, and there is option like a HDL wrapper. We have to convert into the HDL code. So give it OK. Yes. So now we can see that there is a adder test is created as a wrapper. Is like we can see previously it was a DB BD block design. Now it is converted into the .v. So this is what your wrapper module, which will be having 3 blocks. Now what I do is you can see the hierarchy adder top and L1 L2. Adder top means this block, and it will be containing these two also, that will be created as a adder test. So now I wanted to make this one as a top level block, set as top level block. I have to make it as a top level block, set as top level block. And if you elaborate this, you can see that the block here under which, and if you elaborate this one also, we can see that there is a adder top block is there, which if we elaborate, there is a adder top Verilog module which will be added with the L1 L2. Means L1, this is what L1, this is what L2, this is what your adder top, on which like you will be having these two integrators like IPs. So this will be having a two IPs. This is a ILA IP and VIO IP. So this and all blocks will be now under the adder test wrapper. So now this is what the B file which we have it, wrapper file we have it, and need to be added with the constant file. So now give the now add over here with the create a constant files. Give it OK. Create file and adder test underscore xtc file. I will be creating xtc file over here and finish. Yes, I will be creating xtc file over here. So it is nothing but port mapping across the FPGA ports that we have. So what port mapping we have to do is, there is a wrapper that I have created across this one, and what I do is I have to create a XTC file that gives the indication that where you will be accessing this all inputs and outputs. So I will be having only clock that I come from the only clock that I comes from the external and generates the anode and cathode. Means I have to give the declaration for the input port from where it will be located. So this is one port as a clock, there will be two ports as a anode and cathode. So now what I do is I will be going with the reference website, right? Reference website. From this one there is a FPGA kit XTC pin details that will be provided over there. So the clock pin which will be located at N11, right? So I will be taking the pin details of the clock and I will be copying it over here. And also one thing we have to remember, the clock pin is the name of clock, but if you see that block diagram over here, the clock which is generated over here with the name of clock underscore 0. So be careful that the same input are you giving over there or not. If the clock is the input that we used in our design, but after you do the wrapping, there is a input that is renamed as, this is the clock name, but which was like a preferred, like we have used it in our design, but this is the name which is created over there, that name itself we have to use it on the XDC. Yes, there is a, there is a mapping for the clock is done. And now remaining ports, if you see it, I have to drive the 7 segment display. That's why, like, let me take these ports, all ports. So let me take like node file. Yes, let me take a node file. So let me paste that. Yes. So now this and all port names as digit and 7 segment, but our port details are, so we need to map with the name of anode underscore 0, cathode underscore 0. So this name, this is what my digit as a anode name, right? Let me replace with the, my name is anode 0, replace all. In the same way, this need to be replaced with the cathode underscore 0. Yes, replace all. Anode underscore 0 and cathode underscore 0. The mistake across this one is G2, which will be located at A with the cathode of 0, but we wrote the code in the small change across the code is, we consider that A is a LSB, A is the MSB, right? So here we consider as A. So we wrote the code like that. A is considered as a MSB. A is located at a G2. So A is located at a G2, which is considered as a MSB. That's why not at cathode of 0. I have to give the cathode of 7th port to be at a. So 6, 5, 4, 3, 2, 1 and 0. Yes. So now this code, let me copy it over here, and the XTC file need to be updated with this one. Yes. Uh, so this is the total XTC file for the 3 ports. The clock is the one port, anode is the another port, cathode is the another port. So let me save, and let us go with the same procedure, like generate a bit file directly. So after we generate a bit file, we have to go with the hardware manager. Uh, this is what device utility, right? How that lookup tables are utilized. Open hardware and make sure that the particular FPGA kit need to be turned on. The particular FPGA kit need to be turned on. Yes. Yes. And then open target auto connect. And program the device. Okay. So this is how initially it is displaying the 0000. Yes. So what we do is, there is a VIO block, we have it, virtual input and output. So actually we need to give all the input combination from these switches. But there is a lack of 32 inputs that we use a VIO block. We know the purpose that why we go with the VIO block. And there is a add probes that we have, and we have to add all the probes and give it OK. And what we do is we will be giving that all the inputs from this one. So there is a reset button, there is a input A and B. So what I do is that I will be giving a 110 input over here, and the sum with another combination of 000, that total sum will be 1011, and like 0110 is the sum that we can see it over here. Carry will be 0 as it is. So let me keep that another input B also 0001. So the total sum is there is around like 110, and which 1 there will be 111 will be the sum. So let me go with another combination 121, 122, that will be the one combination, and we added with the 1, there will be sum of 123 has to commit over here. So there will be 123 has to be display. So we can see that same display over here 123 with the sum of 122 plus 1, 123 display we can see it here, and even we can see it across the logic analyzer also. We can see that the same thing across the logic analyzer here, and there is an option like a run. You click on the run, so the same results we can see it over there on the logic analyzer also. Yes, so there is a input combination that we have applied is um, 112, that will be the one input, and 001 that will be the another input, and we got the sum is around 123, and the carry is 0. So like that we can do that adding up, we can do that addition across like adder circuit which we have implemented on the FPGA. So now this is the total procedure that we have observed for when the number of inputs that we have it more than the number of switches that we have, right, more than switches that we have, such kind of block, how you will be doing the implementation on the FPGA, and how you can see the display across the 7 segment.